Hello everyone. In lecture 3rd, I am going to discuss about thermal diffusivity, boundary and initial conditions. In my previous video, that is lecture 2, I have derived the expression for heat diffusion equation, and there I have come to one parameter that is known as thermal diffusivity. In this video, I am going to discuss this thermal diffusivity in detail. So, I have defined my thermal diffusivity as Ky rho Cp, where K was my thermal conductivity and rho was my density and Cp was my specific heat. In a more physical way, we can say that thermal diffusivity is a ratio of amount of heat conducted to the amount of heat storage. If any material has a thermal diffusivity higher, that means the amount of heat conducted is higher as compared to amount of heat storage, where in case where the thermal diffusivity of any material is lower, then its amount of heat conducted will be lower and the amount of heat storage will be higher. To understand this concept in more detail, I have considered two blocks, that is block 1 and block 2. Block 1 having thermal diffusivity of alpha 1 and block 2 having a thermal diffusivity of alpha 2, where alpha 1 is greater than alpha 2. So we can consider our block 1 as a copper and block 2 as a brick. From the table here, we can see copper having a thermal diffusivity of 113 into 10 raised to power minus 6 and brick having a thermal diffusivity of 0.52 into 10 raised to power minus 6. So the thermal diffusivity of copper is much higher than the thermal diffusivity of brick. And if some mean you are able to generate a heat generation, that is Q dot inside copper and brick, and they are equal, that is Q dot in copper is equal to Q dot in brick, and it can be done or achieved by placing a heater inside the copper block as well as in brick. So after some time, when the steady state will reach, you will observe a temperature profile within the blocks as shown by a black line. At the center, you will have a maximum temperature, and at the wall, it will be having a lower temperature as compared to center temperature. But due to the difference in their thermal diffusivity value, the temperature profiles and their value will be different in both the blocks, or we can say there will be a significant difference between the temperature profile that is in block 1 then block 2. So due to this difference in thermal diffusivity, we will observe that the maximum temperature in block 2, that is in case of brick, will be higher than the copper block, and this is because of the reason because most of the heat in copper block will be conducted rather than storage. But in case of brick, most of the heat will be stored rather than conducted. That's why the maximum temperature in block 2 will be higher than the block 1. And same will happen with the wall temperature. The wall temperature in block 2 will be higher than the block 1. And we can also observe that the average temperature of block 2 will be higher than the average temperature of block 1. That is T average 2 will be higher than T average 1. That is this temperature T average 2 and this temperature is T average 1. That is average temperature of whole block 1 and block 2. So we will observe due to the low value of thermal diffusivity in case of block 2, it will having a higher average temperature as compared to block 1. Now let's discuss about the boundary condition and initial conditions. In my lecture 2, I have derived a heat diffusion equation for isotropic and homogeneous material, that is as follows. That is, this equation is second order in x, y and z, where it is in first order for time, and alpha is the thermal diffusivity. Now let's further simplify this equation for homogeneous and isotropic material as one dimensional. So we can rewrite our equation as del square T by del x square plus q dot, that is heat generation, divided by k, thermal conductivity, equal to 1 by alpha, thermal diffusivity, del T by del time. So now we can say this differential equation is second order in space and first order in time. So in order to solve this partial differential equation in any domain, we need two boundary condition in x and one boundary condition in time, that are known as the boundary conditions. In heat transfer, there are mainly three types of boundary condition. First one as Dirichlet boundary condition. Second, Neumann boundary condition. And third is known as mixed boundary condition. In this figure, we have three types of boundary conditions. One with a constant surface temperature, another with a constant surface heat flux, which is subdivided into finite heat flux, and another one adiabatic insulation surface, and another one is convection surface condition. So first one, constant surface temperature, is our Dirichlet boundary condition. Second one is our Neumann condition. And the third one is our mixed boundary condition. So as you can see, in the constant surface temperature, here we have a block, and this surface is maintained at a constant temperature, that is Ts, where in this figure we have a constant heat flux Qs double dot, or its value is equal to 0 in case of insulation. So such kind of boundary condition is known as Neumann boundary condition, and first one as Dirichlet boundary condition. And in the third case, we have a convection boundary condition. So if I will explain it more further, I have a surface that is a solid block, and there is a air outside it. So if there is a heat generation inside this block, So the heat will transfer from the block to the air. So first, inside the block there will be conduction, and then at outside the block there will be convection. So we can write heat transferred due to the convection is equal to heat transferred due to the conduction. Or we can write heat transferred due to the convection, that is H T infinity, that is the temperature of the air, minus T surface temperature, that suppose this is my surface temperature, equal to Q conducted, that is minus K del T by del X at X equal to 0, and suppose this is my X direction. So this will be my boundary condition, and this is known as mixed boundary condition, and this one is same as third boundary condition. So if I wanted to write it, rewrite it, minus K del T by del X at X equal to 0 equal to H T infinity, that is the temperature of air, and this is the surface temperature of block. So basically in our heat and mass transfer we have these three kind of boundary conditions.